So they also very generously gave me a whole hour, so I've put together some things I wouldn't usually think about talking about in the fullness that I'm going to talk about them. And so these are some slightly unusual ideas, I think, but you'll see where we go. And please interrupt, I should say. I mean, we're a small enough group of people here that I think, you know, a number of us will have perhaps, you know, novel things to say and things that can be commented on and so on. I hope the organizers are okay with that, but to me, anyway, I'm very happy if you interrupt me and we can discuss anything, because some things will go through fast and some things will not. So this is work is sort of the kernel of which came out of Elle McDonald's thesis. Elle McDonald went back to Australia to work for CSIRO. She's now working for a startup. Jen Pestana, many of you know, at Strathclyde, also was involved with this work. And Anthony Goddard I worked with for 4 months, one summer. He was an MSc student. So Jen, as you know, is a lecturer in Strathclyde, and Elle is working in industry. But Anthony Goddard was just an MSc student, and he did some of the work I shall show you in this talk. So what am I really talking about? I guess from my perspective, and some of you may disagree, there's a really, really big difference in what we're trying to achieve when we deal with symmetric problems or self-adjoint problems and non-symmetric problems or non-self-adjoint problems. So I'm trying to talk both in PDEs and linear algebra here. So I'm using different terms. But of course, self-adjointness, you know, works in the linear algebra situation as well. We don't have to have symmetry in the sense of the entry Aij is the same as the entry Aji. That's not necessarily what I'm saying. Self-adjointness is a more general concept. And it's, anyway, this is the basic theme of what I'm trying to get at. And why I'm interested in this is because when you try and solve problems, whether they be differential equation problems or not, it seems to me there's an enormous gulf between what we can do for self-adjoint problems and what we can do for non-self-adjoint problems. So let me just comment here. This is just about linear algebra, right? So if you think about iterative methods for linear algebra, right, so if I was to come to you with a positive definite self-adjoint problem, then nobody here would disagree with me that conjugate gradients would be one possible way to try to tackle such a problem. That's why I'm inviting criticism. Please disagree if you want to now, but I think that's a fairly incontrovertible statement that conjugate gradients for symmetric positive definite problems, and I would claim with slightly less ardor that MinRes, due to Page and Saunders, would fulfill a similar role for symmetric and indefinite problems. So there are other contenders there, of course. There's SimLQ and there's versions of QMR, but actually in all the work that we've done on the Stokes problem in fluid mechanics and things like this, we've always used MinRes. This is one thing that Bernd Fischer taught me many years ago, that we were using conjugate gradients when I first started work on this over 25 years ago. And he taught us that this could fail, right? Because you get Ritz values very close to the origin. And we said, oh, we've never seen that. Within a week, we saw it. Within a week, we saw it, and we've been using MinRes ever since. And MinRes is, of course, robust for self-adjoint problems.
I don't know if you want to say something about the indefinite problem.
About the indefinite problem? I mean, the indefinite problem is still self-adjoint to me, right? Even if it's indefinite, it's self-adjoint. The eigenvalue problems that you come to look at convergence are a little more complicated, therefore, because you have eigenvalues on either side of the origin and the constraint point in the middle when you're looking at Krylov methods. But nevertheless, the eigenvectors are orthogonal. That's the important property. The eigenvectors are orthogonal, and therefore you only need to know something about eigenvalues, and you still get essentially I mean, I'll go on a little bit about this, Daniel, but you essentially get what I would say is descriptive convergence bounds by knowing something about eigenvalues. You don't need to know more. When you look at non-self-adjoint problems, then of course, I mean, those of us who lived through this revolution in the 1980s, 90s know that at every meeting we went to, there was a new method or two. And so I list GMRes, Joseph Sard, 1986, by C.G. Stab and Van der Vorst, 1992, I think, is that 3? I forget. You know, CGS predated this, which is another method I didn't even mention now because I don't know if anybody uses it. QMR certainly was used and perhaps is, and IDR is a new kid on the block. Martin van Heijten is here. So Martin invented this with Peter Sonneveld. It's an interesting new method, but there's lots and lots of methods. And in particular, in the late 1990s, there was a whole flood. Every meeting there was new methods and so on. And why? And the answer is because there's no best method. There's no best method. There's a very nice early paper by Trefethen and Reddy and Noel Nachtigal, where they give examples of, I think they were looking at CGS and GMRes and conjugate gradient for the normal equations, and they give examples where there is each of these three methods outperforms the other two by a factor of at least root n, where n is the dimension of the matrix. So this was just to show us somehow, you know, there is no method that is good for everything. You know, so for example, if you want to solve systems that have an orthogonal matrix and you want to use Krylov methods, which you probably wouldn't, then you probably should use the conjugate gradients for the normal equations because they're pretty easy, right? Whereas you probably shouldn't use GMRes because GMRes hunts for all these eigenvalues around the disk and then it's sort of very slow in general. So they have, anyway, 3 very precise examples where they show that one of these methods outperforms the other two by at least a factor of root n in terms of number of iterations. So in some sense, ramming home, this is an old paper, but it rams home the point I'm trying to make here, that somehow the fact that we have this whole range of methods is because we can't alight on one which is the best, like we can in the self-adjoint case. This is all I'm going to say about preconditioning, actually. Well, I'm going to say quite a bit about preconditioning, but this is really the, you know, nobody here does anyone here need me to explain this? I'm just going to, I put it in quotes because many of us know we don't actually always do left preconditioning with a preconditioner P. But anyway, I would say that for nearly all the methods we use, we require preconditioning. Put the other way around, and sometimes this is the way the PDE people look at it, you know, if you're going to use AMG, you always throw it inside GMRes anyway, right? You always do a Krylov method on the outside, so that somehow it's very rare that you don't. And so we're trying to find preconditioners P, so there's faster convergence of the appropriate iterative method for P inverse B rather than for Bx equals B. Very simple statement. I'm not trying to say anything. Many of us know that we don't do it exactly like this and so on, but this is just the notion. Okay, so let me think about iterative methods for Bx equals C. I don't like Ax equals B. I've gone off Ax equals B because A is a symmetric character, therefore a symmetric matrix. So Bx equals C. So B is my matrix. So what do? We generate a sequence of vectors x1, x2, and so on from x0. And we do it using one matrix vector product at each iteration. That's fundamentally what we're prepared to do. Usually that's why we like sparse matrices and so on, of course. And then, of course, we build Krylov subspaces. You do one matrix vector product with a vector, you're going to build a Krylov subspace. And by doing that, your residuals satisfy, do I have a pointer of any type here or not? Oh, this is a pointer. No?
Yeah,
Oh, this here. Okay, great. And I'll touch, which thing should I touch? Oh yeah, which one should I touch? Because I haven't got my glasses on, so I can't see.
Oh. Okay.
It should be that one, shouldn't it? It doesn't seem to. Oh!
Is it looking at?
I don't know.
Or did I do it?
No, you did it.
Okay.
Oh, it doesn't matter. I'll talk. Oh, right. My Volker's got one. That's great. Thank you. Thank you, Volker. That's great. That's okay. Okay.
Up in the middle.
The one in the middle there, that one. Ah, here we go. Right, okay. Right, so we build residuals which are polynomials in the matrix times initial residual. The residuals are, of course, C minus bxk, where I'm dealing with bx equals c. And these pk are polynomials of degree k or less. And this is the consistency condition that we solve the right system of equations. So if we have a diagonalizable matrix, that's already asking for something that we're not sure of. We have a diagonalizable matrix, then we immediately have that the norm of the kth residual is bounded by the norm of a polynomial in this matrix of eigenvalues, this diagonal matrix of eigenvalues, and the norms of the left and right eigenvectors times R0. All right, so that's a standard estimate you can get immediately from just realizing you're doing Krylov methods, basically. And if you happen to be in the charm situation, so all my B's are, I'm going to say I'm talking about reals. I mean, it could be complex, but I'm just dealing with reals at the moment. If B is B transpose, then X inverse is X transpose. Everybody does this in their first course on linear algebra. Then, of course, this bound just depends upon this. And it's a bound that depends only on the eigenvalues of the matrix B. And then if you have well distributed, or if you like clustered eigenvalues, you get fast convergence if you've got this symmetry. So here there's no mention of indefiniteness or definiteness. This is true whether you have indefinite or definite, as long as you have symmetry, self-adjointness. Okay. Let's, by contrast, look at the situation for GM-res. So in other words, if I have a non-symmetric system, then here's the eigenvalue-eigenvector bound I just gave you. That this is the relative reduction in residual, is bounded by, here's the condition number, if you like, the left eigenvectors and the right eigenvectors, and here's the polynomial in that diagonal matrix lambda. So this is the minimum over polynomials, this is the constraint condition, and the max and lambda j are the eigenvalues, right? So the difference you can see here is you simply don't have this factor if you've got self-adjoint problems. This is just one, right? And so you just have to worry about eigenvalues and whether you can get eigenvalues for which there are polynomials that are of low degree for which are small. Here's the field of values bound. So if 0 is not in the field of values, the origin is not in the field of values, then this set, right, you can get this bound, where now instead of looking at eigenvalues, you look at point z in the field of values. And now you've got a much nicer prefactor, 2 instead of this possibly large number, but now you've got a much larger set typically, right? So that's the difficulty with a field of values bound. It is useful in certain circumstances, and I've certainly used it in proving certain things. There's also, for example, pseudospectral bound. So the epsilon pseudospectrum of B is the set of Z such that the resolvent is greater than epsilon to the minus 1. This is the places, these are the things that are near to the eigenvalues, if you like. And then the bound here is, again, the relative reduction in the residual norm. K is my iteration counter. Is bounded by, and here you go, here's the min-max polynomial on now a set which is the pseudospectral set, different for each epsilon, right? And then L of D, this is the length of the boundary of the pseudospectral set. And this is just the radius, the circumference of a circle of radius epsilon. So this would be 1 if you had normal matrices. You had symmetric matrices, because then these pseudospectral sets would be small balls, small disks around of radius epsilon, so this would be 2 pi epsilon, and so this would be again the same thing. But you can see all of these are the sort of bounds we have. There are others. I mean, go and ask Anne Greenbaum. She will tell you, 5 other different contexts, but just these are the sort of obvious ones in a certain sense, or the simpler ones that people have used in anger. So here we go. The difference between symmetric and non-symmetric problems, I claim partly at least arises because of convergence guarantees. For symmetric problems, descriptive convergence bounds based only on eigenvalues, a priori estimates of iterations for acceptable convergence, good preconditioning guarantees fast convergence, done. You can tell an engineer this will stop in so much time if you have some knowledge about the eigenvalues. For non-symmetric problems, by contrast, to date, there are no generally applicable and descriptive convergence bounds. There are bounds. I've just shown you 3. The question is whether they're descriptive or whether they're very pessimistic for the problems that we're dealing with, right? Even for GMRes, for any of the other non-symmetric methods, then convergence of theory is extremely limited. So there's no good a priori way to identify what are the qualities of a preconditioner in the non-symmetric case. It's a very simple sort of truth, but I think this is a major theoretical difficulty. But heuristic ideas abound, right? I mean, we're practical people. We try to solve problems. So the fact that we, you know, have this difficulty doesn't stop us trying to solve problems. But you see the difference here. This is another thing. Let me go a little bit further. 2 theorems. I'm going to quote you 2 theorems. Some of you know these theorems very well. Perhaps I'm saying them a slightly different way. So here's Bx equals C again. If B is in Rn cross n, is self-adjoint. So I'm just being a little bit more general here. So let it be self-adjoint in an inner product described by a symmetric positive definite matrix H, right? So H is the inner product matrix. This means, this first statement here, means that, of course, Y with Z in this inner product is, well, that's Z transpose HY, that's the definition, right? That's the definition of this inner product. And so B being self-adjoint in this inner product means that BY with Z in this inner product is the same as Y with BZ. In other words, the adjoint in this inner product is exactly the same as the matrix itself, and this is the same as HB is B transpose H. So B is not symmetric, H is symmetric positive definite, right? So that's what this first statement means. If B is self-adjoint in this inner product, then for the minimum residual method, and I'll just stick to that because I'm not saying anything about, this is to do with indefiniteness at the moment, to say. So using the MinRes situation, then the iterates satisfy the residuals in the H norm are bounded by the min-max polynomial, the initial residual in the H norm, well, lambda j are the eigenvalues of B, not the eigenvalues of HB, right? The eigenvalues of B. So, I mean, this thing you've seen now 4 times, right? The minimum of the polynomials of the maximum value of P of lambda. And if B is also positive definite in this inner product, then you can use conjugate gradients, and then the theorem is that the error in the HB norm, so HB is symmetric, that's what this statement says. The error in the HB norm is less equal to the min-max polynomial, again, lambda, and then the error, initial error in the HB norm. And again, lambda j are the eigenvalues of B, not the eigenvalues of HB. And why does this make sense? This makes sense because there exists an H such that B is self-adjoint in this inner product if and only if B is diagonalizable and has real eigenvalues. So that's why this makes sense. So I'm just saying, there's the slightly more general context of you think of self-adjointness in its most general context here. That is, every inner product on Rn is an inner product of this form. That is, there exists an H. So this is a general statement in some sense. All right. So,
I have a question. I don't know the answer. So the use of this with a different norm. So H is symmetric positive definite, but could have very high.
Sure. Oh, I'm not advocating this.
No, I was just wondering. I'm just not criticism. Just wondering. So this is a way to move the condition, possible conditioning of the base of the eigenvector base B into the norm.
Yes. Yes. Precisely.
That's what you guys do all the time.
It's precisely, that's that. Yeah, yes, I think that's right. That I think sometimes norms are invented in the PDE context that do this, in some sense. And there's a, yeah, I think Volker's right, that's exactly what you're doing. I mean, I make more statements about this. I mean, you can construct H's, they're non-unique. I mean, there's an existence theorem, not a uniqueness theorem, absolutely not. I mean, just think of examples involving the identity matrix and you realize very quickly they're non-unique. But you can build these H's by looking at eigenvector matrices. So, yeah, I mean, it's borrowing from Peter to pay Paul in some sense. I'm not saying you're making an advance, I'm just saying this is the most general statement you can make about matrices which are self-adjoint as opposed to matrices which are symmetric.
But in other words, the fact that you're measuring the residual in that norm
Yeah.
is missing.
Yeah, absolutely. It may be a very poor norm to measure it in. Absolutely. But again, in the PDE context, just like Volker indicates, there may be some reason to think, you know, that you're solving an advection diffusion problem or something. There may be some reason to think that you want to have a norm that involves something, the square of the advection or something like that. And they may think that a natural sort of norm. I mean, you've looked at some of the aspects of my book, I know Valeria, so you know that my attitude is, here's the PDE, this gives you a norm, and that norm, we should use that in the... Yeah.
This is like you're taking just a piece of the operator. You're not measuring two norms, you're always measuring.
No, but I guess, sorry, I really know it's a very general statement, but I think the example, you could have something which is self-adjoint essentially in, you know, n-2 dimensions, and then in 2 dimensions it's not, right? You have something that's completely diagonalized by orthogonal eigenvectors, then you have a Jordan block in the corner, right? So I'm just saying that the previous estimate looks very, very crude in that sense. I'm just saying here you could perhaps use this a little bit more precisely to help you. But all I was trying to do here was just say, here's the most general theorem I can do. It's not that the previous theorems that I've shown you are in any sense deficient. I'm saying that basically the same thing happens even if you look at the most general concept of self-adjointness. That's all I'm really trying to say here. But you're absolutely right. It's a question of essentially dealing with the eigenvector non-normality, the eigenvector non-orthogonality, and putting it in one norm or essentially putting it explicitly in the bound. That's essentially correct.
So, maybe this is a naive question, but I would
Absolutely, naive questions are the best ones, right?
if I give you a B,
Yeah.
you have this B that represents your problem,
Yeah,
that is a priori non-self-adjoint.
yes.
So, does there exist a criterion to know whether this B may be self-adjoint with respect to certain
in a product. So here's the statement, right? That's what the statement at the bottom says, right? A real matrix B is there exists an H, there exists a self-adjoint matrix, a symmetric positive definite matrix H, for which B is self-adjoint in the scalar product, the inner product defined by H, if and only if, the very precise statement, if and only if, right, B is diagonalizable and it has real eigenvalues. So if you have a matrix with complex eigenvalues, a matrix that has Jordan forms, then. But that's not an easy statement in practice, right? I mean, it's the truth, but it's not an easy statement in practice to check out. There are situations where, I mean, I know Volker's come across one where you have a problem which is not symmetric, but you can identify relatively easily that there's an inner product matrix or a matrix in which it is self-adjoint. And then I'm just saying you get essentially the same sort of thing. Okay, so there's my first theorem. Here's my second theorem. And this theorem has been known for nearly 25 years. Right? Amazing. And there's generalizations of this, but this is the theorem. And I essentially took this from the abstract for this paper, for those who know this, right? So this is the paper by Greenbaum, Ptak, and Strakosch, 1996. Given any non-increasing positive sequence, this is exactly the way they say it, right? These are values, right? Non-increasing. There exists a matrix and a right-hand side with the norm of the initial vector x0 being f0, right? Being this number, such that these fk's are the norms of the residuals xk, where xk is the iterate at step k of the GM-res method, right, applied to bx equals c with the initial iterate x0. Moreover, b can be chosen to have any eigenvalues. So contrast this extremely negative statement with what was just gone before, which was essentially a positive statement, said what you could do. This says you can't do anything in some sense. It says you give me a matrix that has eigenvalues that are all 1, right? Then I can find you a matrix B, right, and some right-hand side, but so that you can get convergence which is stagnatory until the last step. Right, so Eigenvalues tell you nothing. People interpret this in very different ways, and it's been over 25 years. It's not as if we're, but it defines some of the landscape for us, right? It knows what we have to go around. So that again, I think, you know, to summarize that, if you've got a symmetric system, convergence of iterative methods can be bounded in terms only of eigenvalues. Badly distributed eigenvalues can give you bad convergence of iterative methods. But for non-symmetric systems, even if you've got well-distributed eigenvalues, you can get arbitrarily bad convergence. That's the summary of those theorems. So the consequence, as I say, preconditioning symmetric systems is well-founded. Our pure mathematical colleagues don't mind what we do. It's well-founded, right? Preconditioning for non-symmetric systems is heuristic. Unless your preconditioner can endow symmetry in some way, self-adjointness. All right, I've ran that home a little bit too much perhaps, so let me move on to thinking about some non-symmetric problems, right? So here's a non-symmetric problem. I've tried to write it in a language which, if you're a PDE person, you don't get so worried about all these you know, matrices appearing everywhere. You can think of L as an operator, a differential operator, whatever you wish. Non-self-adjoint problem, right? I'm thinking of solving problems LU equals F, where LU with V, and whatever inner product you choose is not U with LV. So L is not the adjoint of L, right? And you've got any inner product. So the classic examples of these things are, well, convection diffusion problems, or most problems that have odd even derivatives. Right? So that's why we spend quite a lot of time on the convection diffusion problem in the book with Howard Ullman and David Sylvester, for example. Those are hard. You can prove precisely what Valeria indicated, that for very small, if you don't have too much advection, you can show that there are inner products in which these things are self-adjoint, if you have very small advection. And the norms are becoming exponentially skewed, basically, because the inner product becomes exponentially skewed. It's like an integrating factor. And so there you get really bad norms that come out, or inner products that come out of it, even if you use the self-adjointness. I don't really know how to progress with that. I mean, much further than what the ideas are in our book for solving such problems. Here's another type of non-self-adjoint problem, which I am going to make a little more progress with. So these are time-dependent problems, right? So for time-dependent problems, here's the time derivative, du by dt. And du by dt with v, at least if you do the simple L2 inner product, is minus u with vt. In other words, it's a skew adjoint operator, because it's first order. So it's certainly not self-adjoint. So let me violate the terms of my contract here to speak to you in this conference. And first of all, talk about ordinary differential equations. I apologize to the organizers. All right. This is just to give you some ideas. And then we'll move on to PDEs. Right, so here's a linear ordinary differential equation, which all of us could probably write down the solution in, you know, when we were in our nappies. But anyway, that's fine. Let's take this initial value problem, and let's discretize. For example, here's a simple backward difference, and here's a theta method, so-called, right? So you have theta times yk plus 1, 1 minus theta times yk, and you have the initial value. Tor is going to be my time step. I have L steps of Tor that get me up to capital T. That's the final time I want to get to. And I can write down this system as a matrix system, and it looks like this. I have a matrix B. I'll show you the next thing. I have the value y1, y2, y3 up to yl. So that's the complete trajectory for my ordinary differential equation. And then these are the right-hand sides for these things. And B looks like this. So it's L by L. It's a bidiagonal matrix. It's triangular, biangular. B is this number, C is this number. So this is what is a Toeplitz matrix, right? It's a Toeplitz matrix because it has constant diagonals. Yeah, the eigenvalues are very obvious here, right? Yeah. Right. But this is almost an example, a good example for what we just said, right? All the eigenvalues are the same. But we can get arbitrary bad convergence, presumably, for this system, because it's not symmetric. So the non-symmetry of the system is precisely what I'm talking about, right? It's triangular. Fine. We're not in a, you know, we all know that triangular systems, developing triangular systems is a way of developing direct methods, but bear with me. So, once I have a real Toeplitz matrix, then I'm prepared to use what Jen Pestana and I established 4 years ago. The very simple idea, which has been well known for a while, is that if you use this flip matrix, so this is, you can see the identity written the wrong way around, standing on your head, all right? The identity like this, then if you just apply y, this is what I call the flip, to b, then you get a matrix for which the constant diagonals are the constant, the other way. It's a very simple calculation, right? Oh, thank you, anti-diagonals, right? Why are things per-symmetric then? I guess I don't know. I was going to call them the per-diagonals, right? But anyway, that's strange. Anyway, if you do this on the back, you get it this way. If you do it on the front, you get the A-1s here and the A1s here and so on. It's whichever way you do it, right? What can you spot about this matrix? It's symmetric. Rather perversely, but it's symmetric, right? So as long as I had a real matrix to start with, if it's a complex matrix, this doesn't work. As long as I had a real matrix to start with, this is symmetric. So the one thing I now know is its eigenvectors are orthogonal. MinRes can be robustly applied. It's a symmetric matrix to By. I've never come across such a matrix that's not indefinite. So that's why I'm talking about MinRes. I'm interested if anybody knows of any such example where they're actually positive definite, but I haven't actually looked at it, but it's probably not true, not possible. So the convergence of MinRes will depend only on the eigenvalues. And this matrix is this so-called, this matrix is called the Hankel matrix. And Hankel matrices are well known to be really nasty matrices, right? So the eigenvalues are really badly distributed. So we have to precondition these matrices if we want to solve these things, and so this preconditioning has to be symmetric and positive definite for a self-adjoint problem in order to preserve the self-adjointness. So fortunately, now we're in the realm of Toeplitz matrices. There's been theory that started off with a suggestion from Gil Strang in 1986, and there's various other people. This is Tony Chan, this is Raymond Chan, this is Eugene Totichnikov. I've missed out many, many names. But there has been a lot of work on Toeplitz matrices, and it's well known, and Gil Strang's proposal was that you can approximate a Toeplitz matrix with a circulant matrix. And a circulant matrix is just a discrete convolution, and a circulant matrix can be diagonalized by a fast Fourier transform in this amount of work. That's typically what's going on, right? So we can actually diagonalize. These things are complex objects, so I put a star. But you can diagonalize circular. So there are different ways of doing this, and so there's the Strang way, or there's the so-called optimal way, which is the Tony Chan way of generating a circulant from a Toeplitz matrix. Simple example would be to take your Toeplitz matrix, throw away all the stuff in the outside, and then wrap around the inner things to make it periodic. That's Gil Strang's way of doing it. Anyway, there's many ways of doing these things, it's well known. And what they could prove in the symmetric case was that if you use such a circulant as a preconditioner for such a Toeplitz matrix, then the result is a identity plus a matrix R which has small rank plus a matrix E which has small norm. So there's quite a lot of statements of this type. I'm being quite general here in some sense. I mean, I'm being correct, but if you want more precision, there is more precision in what I'm giving you. That's what I'm trying to say. So what this means is the eigenvalues are essentially, I plus E is like a matrix identity plus a small norm, so these are in a small ball about the origin, and then small rank means you can have a few outliers, right? Because of the rank. So this is really I think a marvelous piece of theory because, we're so used with conjugate gradients to trying to prove that the eigenvalues are in a particular interval. And they're not in this situation, but actually they're still wonderful preconditioners, these preconditioners, because they give you only this small leakage of outliers held in this, relevant to this matrix R. Right? Eigenvalues are clustered about one except for a few outliers. Well, that was true in the symmetric case. So I'm just going back to ensure positive definiteness in the case we're using By, remember? We can just introduce the absolute value of the circulant. So the absolute value of the circulant is a circulant. Fortunately, it's exactly this, where the absolute value of lambda just means literally you take the absolute value of the complex eigenvalues. And this guy here is real, symmetric, and positive definite. And because the FFT gives you a diagonalization, this is done in n log n. Usually the absolute value of a matrix is a disastrous object as far as I'm concerned. It's a really awkward thing to get hold of. Whereas here, because you have a thing that strips out and diagonalizes it for you, it makes it easy. Okay, and so this is the theorem that Jen and I proved in 2015. If you take this absolute value preconditioner for By, then what you get is J plus R plus E. R is of small rank, E is of small norm, and J is an orthogonal matrix, a real orthogonal matrix with eigenvalues of plus and minus 1. So there's the indefiniteness coming for you. The preconditioning essentially has to be a congruence transform, so you can't change the inertia. So you'll get the same number of positive and negative ones as you get for as the inertia of the original matrix. But what this tells you is you're going to have fast convergence because min-res convergence depends only on eigenvalues, right? And these eigenvalues are clustered around plus and minus 1 except for a few outliers. That's what this theorem tells you. So here's the ordinary differential equation. This is the number of time steps. This is the condition number B. These are not nasty matrices, right? No, nobody's saying they are, right? 30 rather is not a bad condition number. The number of iterations is 4. I didn't go any further because the number of iterations is 4. And the condition number is about 30. So the square root of the condition number is about 6. Right? Yeah, but it's not symmetric. Think Greenbaum-Strauss attack, right? This is the natural thing. Eigenvalues tell us things. Well, they don't in this case. I've done something slightly complicated to a triangular matrix which has one eigenvalue.
It's already the worst case.
This is, what do you mean the worst case in what sense?
The bidiagonal with one eigenvalue
Yeah.
is already in principle.
That's why I did get to my introduction, to try to get you thinking that this is not any more easy or more difficult than any other thing, I think. I mean, if you think about it, every matrix has a Jordan form. We can't compute it as numerical people. These are just bidiagonal matrices. Right. What happens? Yeah?
Can you say in advance the rank of R?
The theorems don't tend to say that. The theorems are of the form, as far as I know, the ones that I've seen, there exists a rank R. Lothar may know more about this than I do. I don't know. I mean, there exists a rank R for which the rank of the matrix R is less equal to R. I don't know of any explicit bounds on what that is in general. Though there may be specific theorems in certain cases, I don't know.
Because small is a relative
Yeah.
term.
Yeah, sure. Yeah, so I'm
100 compared to 1 meter.
yeah, sure, absolutely. I mean, so I think, you know, what these, the set of people in this area did was they did computation hoping they'd find the eigenvalues for Strang's suggestion would be in an interval. They thought, oh no, they're not. You know, they're not in an interval. There are these things that straggle out. Typically, but I mean, I don't know what a typical matrix is, but we see in our computations like 3 or 4, sometimes 6. You know, almost regardless of dimension. But there are no theorems that say that will be the case.
So I don't, it's the first time I've seen this Greenbaum result, and but you also showed the other results which involve the eigenvectors and which involve the field of values. So I mean, you painted always as a very negative result, the Greenbaum result.
Yeah.
I mean, for a specific matrix.
Yeah.
You checked whether these matrices, this one in particular, actually has bad eigenvectors, has bad field of value. I mean, does it?
Well, this matrix essentially, I mean, if you look at it, I mean, this matrix. Oh, I see. So I've not got the thing in, so I have to go this way. This matrix. Oh, going the wrong way. Here's our matrix. So this matrix is bidiagonal with one eigenvalue, right? But this is essentially a Jordan block, right? It's one Jordan block. So it's not diagonalizable. Full stop. It's the worst case, exactly as Volker says. It's one Jordan block. I mean, I'm not giving the Greenbaum-Strauss theorem to to do anything other than just to tell you some of the difficulties we have in getting around to producing any kind of convergence theory for non-symmetric problems. We simply cannot do it based only on eigenvalues. That's all I'm trying to say for it. I mean, it's a theorem. You know, it's a piece of the architecture. It's part of the landscape. We have to circumnavigate that in some clever way. Martin?
You can make it diagonalizable by using a different time step in every step.
So this is one thing that I know you and Barbara Volmuth and others have done, is that if you simply, I've got this because you can see my B here has got the same tour, the same time step for every step. That would be perhaps the most usual thing to do, but you don't have to do that. And as Martin exactly points out, if I make this different for every step, then these numbers are all different. Then this matrix you can prove is diagonalizable, and you do. And so there's work in this direction, and you can then diagonalize this matrix, and then you can, you know, you're not in the same constraint as I'm in by using the same time step.
And the answer to Valeria's question is essentially the number of Jordan blocks, the maximum number of Jordan blocks you have to one eigenvalue. Exactly. That would be the right. Because you can, in principle, the maximum number of Jordan blocks that to one eigenvalue. So if you have one eigenvalue, and then in this case it's rank 1, and then if you have 5 Jordan blocks to one eigenvalue, then you can make a block circulant matrix to precondition each of them in this way, like you have here, and so that's what we do.
Oh, I see. You think that would be the rank? Oh,
Because you're talking about convergence of total symbol.
No, but I mean, just the question: if you would construct a circulant preconditioner that do the best, the lowest rank, that's the lowest.
I don't quite follow, but we can talk about that. I don't know if Valerie does. Maybe somebody's cleverer than me, but I don't follow. Quite.
The standard very high end here.
What?
You're putting the standard very high.
Well, okay.
I'm just working on my slides right now.
Oh, okay. Well, I've got another 3 hours, haven't I? Is that right? Oh, so Edwin.
So would you actually prefer the case where you use a different time step so that you can diagonalize, or you actually prefer
so that's the choice of the person who wants to solve the problem, as far as I'm concerned. That's one way of doing it, absolutely. And this is another way of doing it. If I don't use the same time step, I can't use Toeplitz matrix technology. So, you know, it's horses for courses in some sense. I mean, you can choose. That will depend on what computer you're using, what your problem is, and so on. And these are two of the possibilities.
But is your feeling that it's actually easier to use the same time step and use your preconditioner, or?
I think there are problems. You see, I mean, if I put my PDE hat on for a while, there are problems for which you want to use a constant time step. And so, for example, if you have a wave problem, you're looking at, the waves radiating from some body or something that you irradiate with some radar or sonar or whatever, then because you've got a frequency, then you're going to probably want a pretty constant time step. This might seem sensible. If you...
For this model problem, that Alchemist equation of equal time step gives you the smallest truncation. Every variation increases the truncation.
So
it's also fun result.
And I was going to say that if you have...
There's a reason to use the same time step. You sort of break it if you use a different time step.
And if you have a diffusion problem, you're often tending to some steady state, then you presumably want to lengthen your time step as you get towards it. Using constant time step would be crazy. So I think there are different situations in which you might think it reasonable.
I'm just thinking from the linear algebra point of view, it's actually harder to solve the problem if you have different elements of the.
I'm just saying there is literature on that, and Martin certainly contributed to that literature. I mean, I'm not an expert, but.
Is as good as equal.
Oh, okay. Somebody's supporting my cause anyhow. Right. So where am I going? Done that. I've done that. Done that. Done that. Oh yeah. So, those of you who are interested in multi-step methods, ODEs, I'll get out of ODEs, right? It's the same sort of thing. If you have BDF2 here, you can build the system and the matrix looks like this. It's a real Toeplitz matrix. You can do exactly the same thing. It now is tridiagonal, but still triangular, of course. And, sorry, should we close these blinds? Can I just?
Yeah, we'll get into it.
Okay. It's not a manual. Okay, okay. So these, again, this is the number of time steps, 10, 100, 1,000. The condition is, again, not bad, 67, right? This is not a bad time step. Thank you, Victoria, thank you. And the iteration is, again, 6. So that's of this approach. So that, what I'm saying is we've proved and we've observed fast convergence for using an absolute value circulant as a preconditioner for a flipped Toeplitz matrix. And of course, in this situation, we try GMRes as well, just with the circulant on B. Now, this is a non-symmetric matrix with a, well, it doesn't matter, preconditioner, it's a circulant. There's no reason, there's no theory for this, as far as I can see. But it's quicker. We find it's always quicker in practice. That's what we find. And I've tried to prove this and I can't do so. I haven't succeeded in doing so so far. So when I spoke on some similar ideas to this 18 months ago in Copper Mountain, Tim Kelly was in the audience, and Tim Kelly said, you've proved that this is Krylov friendly. So this is Tim Kelly's term, not my term, right? That somehow what we're doing with circulants here is creating systems which are good for Krylov methods, and that's our intuition, of course, that's our heuristic, right, about these things. So all I'm saying is I'm spending quite a lot of effort to prove that we will get guaranteed fast convergence with minres and flipping and so on. And then I observed there's actually a faster way of doing it, which involves slightly less work. Disappointing. Sorry? Oh, what's the statement? Oh, sorry. I just mean it takes fewer iteration steps. Of course, GMRes is more expensive if you take many steps because you have all the orthogonalization. But I just mean, sorry, it takes fewer iterations, this statement. I'm sorry, I should have been more precise.
C is not the same C, because that is the absolute value C.
That's the absolute value C at the top.
Yes, with the definition.
And this is just the circulant, not the absolute value circulant. Of course, going from this to this is almost trivial. It's a question of just doing, you know, just taking the absolute value of n numbers.
Just to make sure that it's,
Yeah.
it's not.
You can do absolute value of C here as well. It doesn't do any better. In fact, it does more similar to that. But it's not a very simple picture. I thought this would be a simple picture because I had a comment from Salima Gurol in Toulouse. That, you know, is it the case that if I use the absolute value here, it would be, again, twice as many iterations as I get there? This is typically half the number of iterations that this is. And the question was, if I use the absolute value here, do I still see that factor? And the answer is no. It's not clear. You know, I'm tiptoeing here through lots of difficulties, in some sense, to try to avoid all sorts of problems. And we can prove something. I'm just saying it's slightly disappointing that we can observe something better. But, you know, I understand Tim Kelly's notion somehow that the fact you've got somewhere where you can prove some approach works, then maybe a nearby approach works reasonably well as well. But that's the heuristic, right? That is not proved. Right, this is what this conference is about, right? About PDEs. So this is the diffusion equation. In a domain omega, here's my time interval. The domain, I don't really care what it is, in R2 or R3. I'm going to have some boundary data on the omega. I'm going to have some initial condition at t equals 0. I'm going to discretize with finite elements with a mesh size h in the usual sort of way, and I'm going to let there be n spatial degrees of freedom. I don't care if you use an irregular grid in space, or you know, use what you use for spatial discretization. I really don't care. So this is just a finite element on some mesh, and this is the sort of discrete equation you get. M here is the mass matrix, it comes from the time derivative. Tau is the time step again. K is the discrete Laplacian, or the stiffness matrix, that comes from finite element approximation of the Laplacian. Okay? PD is done very quickly. But this is a very simple and straightforward process. And then you can generate the system, right? So this is the system matrix, where U1 is now the set of all the spatial variables at the first time step. And U2 is the set of all spatial variables at the second time step. So in other words, this is an n vector. And this is an n vector. And this is an n vector. And L, again, is the number of time steps that gets us L steps of tau get us to capital T. And this, which you might solve by forward substitution, of course. These are triangular systems. If you solve this by forward substitution, it's exactly the same as start with U0, your initial condition, compute U1. Then do U1 and solve U2. That's forward substitution for this system. I could have mentioned that for the ODEs. It's exactly the same. But what I'm not suggesting you do forward substitution, even though these are triangular systems. What I'm suggesting is this so-called all-at-once system has all of the time steps in. These are huge systems, right? Especially if n happens to be large, because your domain is the, you know, car tire or something like this. Right? So A naught is here just this combination of the mass and the stiffness matrix. Symmetric positive definite. A1 is just minus m in this case. I've just done backwards Euler here, just to make. So now I had that matrix here, right? This is a block Toeplitz matrix, right? All of these matrices are self-adjoint, symmetric, positive, definite, these guys. Regardless of what my mesh is, I'm not, for those of you who know about Toeplitz matrix technology, I am not building multi-level Toeplitz matrices. I'm only using the Toeplitz structure on the time discretization. You can use whatever spatial discretization you wish. For spatial parts of problems, we have good solvers, typically, through things like domain decomposition, things like multigrid and so on. That's my belief, and we should use those. So this is our suggestion for a preconditioner. That is, use the block circulant. See, the only difference is this guy. This makes this a block circulant in exactly the same way. I'm making it periodic in time. If you like, if you're a PDE person, I'm taking an initial value problem and I'm preconditioning with a periodic problem in time. Here's the theorem. This is a theorem. This is what Elle, McDonald, and Pestana proved, basically. My name's also on the paper. So if you use this preconditioner, I'll comment about using it, what that means in a while, but if you use this preconditioner for our backwards Euler system, then the matrix is diagonalizable. That's the hardest thing to prove. There's 3 theorems. That's the last theorem we prove in our paper. I've wrapped 3 theorems into one here. If it's diagonalizable, it is diagonalizable, sorry. It has L minus 1, that's 1 less than the number of time steps, times n, that's the number of space degrees of freedom. It has that many eigenvalues of 1. That just says these matrices are somehow nearby. And it has n eigenvalues which cluster around 1 for small h. Again, there is a more precise statement in our paper, but I'm trying to make it understandable here in the context of what I'm saying. All right? In other words, this would not be such a bad preconditioner for this problem. Generally what I take this theorem to say. Martin?
So how does this relate to the theorems about circulant matrices? By low rank or small, because I use the low rank.
Yeah, so these are blocks. All these matrices are blocks of size n, of course, that's right. So I'll come back to that. You have to be a bit more patient, I'm afraid. No, it's fine. No, there's no hand slapping here, right? Don't worry. So here's just a computation, actually an old one, of the eigenvalues of that preconditioned system. It's much harder to compute the eigenvalues, of course, than it is to solve the systems. Here's 1. These are the real parts. We did this in a strange way, so the imaginary parts are essentially a round-up error. But that's just and it's for a small problem because, you know, eigenvalue computation is much harder. So here's the point. If sigma is just this downshift, what Gil Strang would call a downshift matrix, and C is the corresponding circulant. So this one I can diagonalize. In fact, I can diagonalize this analytically. There's really no difficulty. These eigenvalues are the roots of unity, the nth roots of unity, and these guys are just Fourier modes, right? Then the original matrix is just, so this is Kronecker products. I have to learn this to do this stuff, right? So that you get L copies of A0 down the diagonal, and you get sigma copies of A1. In other words, you get A1s in all these positions. That's our original matrix, and our preconditioner is exactly the same, except we have this A1 at the top here as well, hence C cross A1 rather than sigma cross A1. So this is the only difference between these two matrices. And then I use the only thing I know about Kronecker products, that is that the vector product of Kronecker products is the Kronecker product of vector products. That's this statement here. then you can show that PDE is just, which is this guy, is writable like this, where U are these eigenvectors, these Fourier modes, and A0 and A1 are exactly what they were in the original matrix. So this thing in the middle here is lots of copies of symmetric positive definite matrix. This is block diagonal, no question. These are the wrong way round. Instead of having I cross U, which would be lots of copies of U, I have U copies of I, which is a little more complicated. But anyway, I can write down the inverse. The inverse is this, right? So you just take the inverse and you get the inverse of this block diagonal piece, and then these other pieces are the same. So I've written on the top of the page here again. So in other words, to evaluate, and this is what we do in preconditioning, of course, we apply the preconditioner to a vector. That requires multiplication of R by a U cross I or a U star cross I. And is that parallel over n processes? I mean, there's parallel also in the title of this conference, right? This meeting, right? And then you have to invert these diagonal blocks. And I think that's embarrassingly parallel in that sense. Okay, I should say that if the AI themselves are symmetric, as they are for the diffusion problem, then it's you can do, if these two guys are simultaneously diagonalized, you can do something much nicer. But otherwise, if these guys are not, use the technology we've learned for PDEs, for steady PDEs, so things like AMG, algebraic multigrid. And the question is, well, okay, so we've proved that this was a reasonable precondition, and now I'm saying, well, if you could apply this, if you can do these two things reasonably fast, then you can actually apply this preconditioner fast as well. And this is where my MSc student, Anthony Goddard, came in, because referee comments on the paper with McDonald and Pestana quite recently said, well, you know, is this parallelizable? And we had no way to know if it was, so I set this for an MSc student in the summer. And this is what Anthony came up with. And it's all on GitHub if anybody wants to have a look and see if they can do anything with it. So these are times in seconds for solving this problem with the block circulant I've just shown you for the A backwards Euler. This is the number of processes. We had for an MSc student, you know, you've only got a month to get access to a machine, sort of thing. So we had to use the only machine we could get, which had 32 processes. This is the number of time steps. This is the number of spatial steps. They're not regular grids, they don't have to be. Right? And this is the time. So if you, for example, look at the last row, you know, students never produce vast tables of numbers like this and try and expect people to summarize them. Let's just look at the last row here. This is 1,440 time steps with a spatial resolution of 1,568. Not a fine mesh, certainly not. This is a small parallel computer we have in Oxford in the math department. And so it took this amount of seconds, CPU seconds on one processor, and it took this amount of CPU seconds on 32 processors. And 63.30 times 32 is actually smaller than that.
How come the time between p equal 1 and p equal 2 is more than half?
So this is to do with memory and so on, right, on this machine. Right, I mean, I'm not saying that these are highly tuned or highly explained parallel results. I'm just indicating that this is gobsmackingly obviously ideally parallel.
And what's the spatial solves?
So the spatial solves in this one are done with, good question. I've got Anthony's paper with me. I'll have to have a look. I think it's AMG, but I can't remember. I can't remember. Let's look after it, Andreas, because I can't remember, honestly, I don't know.
How would it compare to a method where we solve time step after another? Like it could be a direct method.
If we used a direct, yes, it could be a direct method in a sense. Is that what you're saying? I mean,
yes.
I mean, even if it was a direct method, I think
it's substantially faster than time stepping. It's substantially faster than time stepping. Yes. It's about, maybe about 15, 16 times faster. Yes.
these are very unusual ideas, as I say. I'm trying to tell you, you know, we've all learned, I teach students they should do LU factorization to solve systems of linear equations. They should create triangular systems. Because back substitution is so easy. The back substitution is not parallel. Basically, that's your basic difficulty. It's highly sequential.
This is why I asked for sequential.
Yeah, yeah.
number of processes than if you parallelize in time.
Yeah, that would be true.
Time parallelization is much faster than space parallelization and time space. That's the statement.
Oh gosh, I'm getting closer. All right, okay. I'm going to have to shut you up a little bit now. You can ask me questions in lots of time. This is the more interesting set of results. This is for the wave equation. So this is for the wave equation where you essentially see something similar. The wave equation is known to, I mean, hyperbolic problems are known to be much more difficult to get parallel solvers over in time. So I think this is more interesting, actually. And this is for a particular discretization, which I've not even talked about. Multi-step methods, similar. More complicated, but similar. You can do, this is the answer to Martin's question, you can create this curly Y, which is Y cross IN. Right, see lots of identities like this. Right, well, Y is the guy as before, and that symmetrizes your block Toeplitz matrix if you have symmetric blocks. So that can be done. When the AI are not symmetric, for example, for the wave problem, then you have to use you have to use solvers for these non-symmetric blocks. So here's the theory: min-res for the absolute value of PYA, this curly Y, is guaranteed to converge a number of iterations independent of L, independent of the number of time steps. Whenever you're going to do this, you have to prove that, right? If it takes L, if the number of iterations depends on L, then you might as well not bother doing this in the first place. So very few min-res iterations required. GM-res with P does better. There is no guarantee, as far as I can see. I tried very hard. AMG, we use Ivan Notet's AMG as an approximate solver in space. Here's some numerics for the heat equation. GM-res, this is with exact solves on the blocks, does extremely well. This is what we can prove. Sorry, these are the sizes. These are the numbers of time steps. I went very crazy here and went up to 2 to the 14 time steps. This is the number of degrees of freedom altogether of these systems. So these are 69 million in this one. But I mean, with this many time steps, you know, that's a little, I don't know why she went this far, but anyway, she did. Okay, but nevertheless, you can see, this is what we can prove. This is what we can prove. Right? And if you do the AMG, this is flexible GM-res with this Ivan Notet's AMG, then this is what happens, which is still not bad, I think. That's for the backward Euler. This is for BDF2, it's essentially similar. This is for convection diffusion. Now I can't do min-res because the blocks are not symmetric. And so GM-res does a little bit worse, and AMG does a little bit worse. Control. I don't know if you have time to do control. There's a control problem. We're trying to minimize the difference between Y and some desired state. We use some control U to do so. This is the heat control, so you're just adding heat sources and sinks in the domain in this case. There's an adjoint PD associated with this forward heat equation. This is the adjoint equation. So P is the adjoint variable. I'm going to use backwards Euler in space. Let me do this quickly. We do discretize, then optimize. It would be the same if you did it the other way around. You get a block system that looks like this for the control problem, where essentially these M's are mass matrices, and these K's, this is the forward evolution of the problem, and this is the adjoint, the reverse evolution of the problem. And the main issue is that this K looks like this. It looks just like the matrix we just had for solving just the heat equation, okay? So this block here, these are all of size n by n, where that's your spatial number of degrees of freedom. That's what sits in here, right? So this is a very large dimensional system. You can do matrix vector products easily. You don't build this matrix ever, of course, you know. And so the main issue is how do you do a shear complement approximation? We do it via what is called a Pearson matching idea, which is to do this approximation. Some of you may have seen it, some may not. So that's in a paper by John Pearson and myself, 2010. Very similar ideas in Schubel and Zulma, 2007, I should say. So I don't want to not mention that. And this is my final slide. This is numerics for the heat control problem with 20 time steps and different numbers of different H, right? This is on a regular mesh, actually. This is for the same H and different time steps. These are the number of degrees of freedom overall, and this is the number of GM-res iterations for the control problem. these enormous problems. Right, done. These are my references. This is the main paper that appeared in CSIRO last year. This is the paper by Jen Pestana and myself from 4 years ago where we prove non-symmetric Toeplitz matrices. This is Anthony Goddard's work, appeared in Etna this last year. And this is my preconditioning review if anybody's interested. And David Keyes has sent me an email to say he apologizes, British Airways cancelled his flight. But he, KAUST, supported Elle McDonald. Actually, she was my last student through KAUST. Done. Thank you. She hasn't asked for questions yet, and Valeria's in there.
So how much all this depends on the fact that you have constant coefficients in your PDE?
Absolutely, absolutely. So I gave a talk in Sparse Days a few months ago where I talked precisely about that issue, whereby if you take a Toeplitz matrix and then you vary coefficients or you vary time steps a bit, so you get something that's not quite Toeplitz, what happens? So that's another question we're investigating. And the answer is, of course, it gets worse. It doesn't seem to get worse very quickly. It will eventually, of course, if you add bigger and bigger perturbations, you essentially got no Toeplitz structure at all.
But you're willing to keep the procedure?
We have not done so, but I mean, I don't see why. I mean, that's the fundamental question, as you say. I mean, just take my ODE, y prime equals ay plus f. Make a variable coefficient. So we make a, a times 1 plus 0.1 sine t or something, right? And then you can you get a non-Toeplitz matrix. You can easily average along diagonals to make a Toeplitz matrix, which you ignore. But then you make a circulant out of that Toeplitz matrix, and you use that or its absolute value as a preconditioner. That's a feasible way to do this. We have not done that for the PDE problems yet. Maybe it could be done. I'm just saying that, so we have to focus quite a lot on perturbations of Toeplitz systems. How much do these things go away? How much do you lose these properties? They don't, fortunately, just go straight away. It's not a very specific thing. If you do small variations, then yes. I mean, I've got my talk from Toulouse, if you want me to show it to you later on in the week, where I can show you some of these perturbations, some of the results. So this is not something to see immediately, but you've got to stay fairly close.
Yeah, 2 comments on this. So I think there's 2 things here which work in favor of you. That's one is that you make the boundary value problem preconditioner for an initial value problem. So
yes.
The circulant thing is what you say.
Yeah.
But the second thing is you get an easy hand on the absolute value. So if you really would use the absolute value of
the general matrix, that'd be horrible.
Preconditioner, if you could, you get super fast convergence. So that's we just have a paper in CSIRO on this. So
okay.
the question is you can't get it. So the question is you have to somehow approximate it, and then again you are in the game how far you can go.
Oh, it's absolutely true. I mean, this Jen and I were thinking about this work from a totally different point of view, and I mean for this second paper here, it was literally going down the stairs to coffee one day. I said, why don't we just get the absolute value, And she looked at it, she said, yeah, we can do that. I was amazed because the absolute value in general is a really awkward object, right? It's much more awkward to compute the absolute value. But when you have a precondition that involves diagonalization, like the circulant does, it's not any work at all.
In the beginning of your talk, you mentioned, basically you said don't use CG, use MinRes instead.
Oh, for indefinite symmetric problems. That's what
you had symmetric positive definite.
No, I'm not. Sorry, I'm not arguing for that, Lothar. No, I wouldn't argue for that. I've concentrated on MinRes because almost all the problems that we get, which are symmetric, but we've never found one that's definite. In all that we've done, they've always been indefinite. That's why I concentrate on MinRes. If you've got an SPD problem, use conjugate gradients. It's cheaper.
Well, yeah, I mean, it may depend on how close the closest eigenvalue is to 0.
Sure, maybe.
I mean, then CG may have.
CG has so many advantages. You know, in my book we praise CG because for the PDE you want to work in this norm, CG works in this norm, you know, preconditioning doesn't change the norm. Use CG if you can, absolutely. Sorry, I'm not arguing for this in MinRes, I'm just saying I don't regard it as much more difficult to use MinRes for an indefinite problem. That's a little bit of a gold statement. You know, please don't think that I'm saying that there are no difficult symmetric problems left. I'm steering clear of the Helmholtz problem like as far as you can believe, because I believe that's one of the really hard problems. You know, there are really tough symmetric problems, and we're going to hear about a lot of those this week, and you should absolutely, you know, work on good preconditions of those things and use conjugate gradients for them, probably, if they're positive definite. If they're indefinite, my view is, you know, if you have things like the Stokes problem, then you can use the positive definite aspect of the 1-1 block in the Stokes problem, and together with a simple approximation of the 2-2 block, and you can use, therefore, solving the Stokes problem is essentially not much more difficult than solving Laplacian.
I mean, in the paper.
But you have to use MinRes.
In the paper about symbol Q and MinRes.
Yes. Yeah. Yeah, I talked to Michael about this a great deal. I mean, SimLQ, I'm using MinRes because MinRes. SimLQ doesn't minimize, right? It doesn't have a very simple, it's a Petrov-Galerkin method in that sense. You're right, the whole paper's about SimLQ. In some sense they said, oh, you could use MinRes at the end. And we say, well, you know, Michael sort of argued with me, said, oh, why don't you use SimLQ? And I said, well, it doesn't minimize anything. And also, of course, it doesn't generalize to GMRes. If I apply GMRes to a self-adjoint problem, I get MinRes. I don't get SimLQ.
Okay. Okay, we have one more question and then coffee break.
It's just a comment. We have analysis for the GMRS variant that you have, but we don't study the GMRS convergence, we study the stationary iteration. And then we can study contraction factors.
Oh, yeah.
Yeah. And so this gives some information on how the method not work with GMRS, but at least for the stationary contraction polynomial, we can get estimates.
I mean, there's this old estimate, you know, came out of Howard Ellman's thesis, right, which is the GMRS1 estimate.
Yes, yes, yes.
Which is essentially the stationary estimate you're talking about.
So we have some results in that direction.
Yeah. No, all these things are valuable, gosh,
and there is another comment. We also have a variant of this method for the nonlinear problem.
Okay.
And in that case, it's not the Toeplitz matrix anymore. You lose this structure because it's nonlinear, and then we approximate by a Toeplitz matrix, and we also have an estimate in that sense. Yeah.
So this is a new Jacobian?
This is not this is the Jacobian. That's then going into the matrix.
Right. Yeah. So these are other ways in which you get variable coefficients, essentially, like Valera is identifying.
Yes.
We've done it in a very simple way of actually introducing variable coefficients. But of course, nonlinear problems will introduce variable coefficients in the linearized Jacobians and so on.
And there we see that if it gets very different, then it gets worse and worse.
Oh, I see. Yeah, sure.
So we have to have a shorter time interval where the Jacobian is very similar still as a good approximation to the real Jacobian. Okay, very great. Very nice talk. I enjoyed it very much.
We've not investigated, you know, I mean, there are many, I mean, really, you know, I don't disagree with any of what is being said here. I'm just trying to suggest, you know, some ideas, some way of looking at things are rather different, right? I mean, you know, if I was standing here in front of an audience of sparse direct people, I have to be really worried because, you know, they think, well, you're solving triangular systems. Why on earth are you using iteration to solve triangular systems? And the answer is it's quicker, actually. Edwin doesn't realize this, but this sort of came out of a comment. The last householder meeting, I asked you a question about, you had this wonderful way of computing the LU factors. And I asked this question about, but don't you have to do this? And you said, oh yes, we have. You had some slides up your sleeve to show that, yes, you could use iteration for these triangular systems. And I thought, you know, and I went away, and that's where some of this came from.
Okay, so I think we'll stop questions for now, and thank Andy for giving such a great talk and nice start to the conference.